Hey guys, it's me, Landon. I'm going to be doing the 6 p.m. recitation today. Before we get started, you're probably wondering why are we on Twitch instead of Microsoft Streams? The reason for that is actually because both of the services, Microsoft Streams and then BlueJeans, are all down right now. It's a huge problem, and we're going to see how we're fixing it. This is the best solution for right now, and we already know how to use Twitch, so that's why we're doing it here. I have a list of things I was going to mention at the beginning. So, new homework stuff. Homework 9, pattern matching, has been released. I believe that's due on Monday, April 6th. So that would be a week from yesterday. After that, graphs have also been released, and I think are going to be due the following Monday as well. So you're going to have you're going to have homeworks due the next 2 Mondays, essentially. Today we're going to cover all pattern matching, so you should be good to do everything on your homework that's due on Monday. And then next week after that, you guys are going to get to do all your stuff for graphs. So going down my list, we're going to be uploading the recitation worksheets, and I think there's solutions as well. Exam 3 is on Wednesday of next week. Make sure that you show up for that. We're going to be doing it online. We'll have more announcements about that and topic list with more information tomorrow. So be tuned for that announcement tomorrow. In terms of answering questions, we're going to do the same format that we did last week, where basically you're going to be asking questions on Piazza in a private post to instructors with kind of the title of the recitation in brackets with the date, and then I'll answer them on stream as soon as I see them. Other things, you can go to either stream as usual. Doesn't really matter. You're already on the late stream, so that's fine. My next thing is the TA app plug. Basically, we are hiring for 30 and 32. The TA app is live, and Jacob and I will be going through the applicants on Friday and late Friday, and determining which people we're going to be interviewing. So if you are interested in the position, make sure to apply on or before Friday. So I just sent an announcement about that a little bit ago, probably about an hour and a half ago or so. So look at that, but that should have all the information. So be sure to apply if you're interested. Also, if you guys need extra practice in the next coming days, the Viz tool, the visualization tool, so that can be found at csviztool.com. It's what I'll be using this recitation to show you guys pattern matching. It's very, very helpful, especially for pattern matching. I think it's one of the most helpful things. Also, another thing is Dr. HB wanted me to mention that she has office hours as well. She never gets any visitors. She would love some visitors if you guys want to visit her in her office hours. Check that out on the syllabus. You can see her hours there. Okay, so I don't have any questions yet, and so I'm going to get into actual content for the recitation. So first off is brute force. I'm going to head it over to the whiteboard. Cool. Okay, what happened to 2-week period for homework during exam week? The coronavirus happened. So because of that, we are really, really limited. And that kind of dead week that we had last week really, really threw a wrench in our ability to space out these assignments. And unfortunately, now we're in a situation where we have homeworks due back and forth like this. I'm really sorry about it. There's not really much we can do. Our hands are tied for a couple of reasons. We have a deadline of when graphs have to be graded. We have to make sure that those are all in by the last instructional day. And we really, really can't push back the exam because of ways that we are amending the syllabus. We didn't want to cause that much chaos. So unfortunately, well, actually, we couldn't move it to the next week anyways, because then I think you still would have had a homework due. But unfortunately, you're going to have a homework due in the middle of studying for an exam. I'm sorry, that's just the way it's going to be this semester. It's weird circumstances for all of us, but we're really doing the best that we can. Okay, so I'm going to get into brute force. So, brute force. Actually, first I'm going to get into pattern matching intro. That's the most important thing. So basically, the question that we're kind of asking with all of these kind of sorting algorithms or pattern matching algorithms is that how can we search for a pattern of length n in a text of length n, right? So we want some pattern, some word, and we're trying to find in a much bigger set of words, is there a match of this pattern, right? So think about if I was looking for all the occurrences of Harry and Harry Potter or something like that, right? Harry would be the pattern, and the entire text of the entire book would be the text of what we were trying to search in. And so generally there are two kind of questions. It's either we're trying to find the first occurrence of a match, that's the first case I noted here, or we're trying to find all occurrences of a match. right? And so there's two different things. In general, they don't require too much extra work on your case for going between one or the other. In all of your algorithms you're going to implement on your homework, it'll be looking for all occurrences of a match. But yeah, that's that. So these are kind of the conventions that I'm going to follow and most other people follow. So it's important to kind of understand those before we dive into these algorithms. So the first is n. N we refer to as the length of the text, right? And that's why I noted it up here of length n, text of length n. I wanted to formalize that below and make sure that you really, really knew that n is going to be the length of the pattern. In terms of n, n is the length. Oops, I wrote length of pattern twice. My bad. Nice, good catch, Landon. So instead of this saying pattern, this is going to be text. My bad. Good catch. So n is going to be the length of the text, as noted right here, and then n is going to be the length of the pattern, right? So generally, n is considered to be much greater than n. The next thing is kind of our conventions for pointers when we're talking about where in relation to the text is the pattern, right? And so I generally think of I as being the offset, as kind of the indent of where the pattern starts relative to the beginning of the text. So it's kind of this indent. And you can see below in this case, I did laughter and then ugh so laughter would be the text, ugh is the pattern. This kind of offset here of two characters of where now U is aligned right here perfectly, that would be our I. So in this case, I would be 2, right? Because 0, if I was 0, it would be, ugh would start at the beginning of laughter over here. But now since it's indented by 2 characters, it's pointing at this character right here. Right, so that's I. I is the indent. The next character is J. And J is the character that we're comparing in the pattern, and we're going to be comparing it to a different character in the text, right? So J is generally going to be between 0 and pattern length -1, and that character is going to be the character that we're comparing against the text. So right here, J would be equal to 1. That means we're comparing character G, right? It's the 0, 1 character, indexing by 0 in the pattern. And then we're always going to be comparing it I plus J in the text, right? So if I look at it right here, I is going to be 2, J is 1. So I'm comparing J of 1 right here with 2 plus 1, 3 right here in the text, right? So that's kind of how this convention is that I'm using the offset here, and I'm kind of circling the comparisons that we're actually going to be doing, right? So basically, the character that we're comparing is directly below where it would be in the text. Hopefully that convention makes sense. I is 2 to line. Yeah, I already said all that stuff. Kind of done with the intro. Unless there are any questions, I'm going to keep on going. There's a lot to cover today. Cool. So we're going to get into our first algorithm. Brute force is our first algorithm. And kind of the basis of kind of these other algorithms that we're going to talk about later and how they can basically improve upon brute force. Brute force, as it sounds, is there's really no optimizations at all. You're kind of just bludgeon through the text with the pattern until you arrive at matches. There's really no rhyme or reason to it. And what that means is you basically line up index 0 of the text with index 0 of the pattern. You compare the pattern while you keep on getting matches. You're comparing the character at text of I plus J and the pattern at J. That's the same convention I mentioned to you on the last slide. And you keep on comparing until, and hopefully you get a match, right? You would get a match if J is equal to pattern length, right? Because if J matched on the pattern.length -1 character, that would be the last character of the pattern. So if J ever equals pattern.length, you've arrived at an occurrence of the pattern in the text. However, if you do not get a match of the pattern within the text, if you get a mismatch, so that would be like if you're trying to compare a character I in the pattern to a character M in the text, well, then the only thing you would do is you would increment I, so that would be sliding I1 along, and I call that generally chugging. Just that's what I say, and you'll see it again when we do it in the Viz tool. And then I reset J to 0. And so I lose all the progress that I had in that entire section of going over the text, of going over the pattern. I lose all the progress. J goes back to 0, and then I start again, right? So I'm going to start comparing it pattern of J, and then the text at I plus J. Cool. And then if we keep on going, if we get through the entirety, pattern equals match. If it's a mismatch, increment I, chug, and set J to 0. And then we just continue this until the pattern extends past the text. And so we'll see that in the viz tool. That's going to look like a situation where the text is over here, and then the pattern is, some of it is clipping off of the edge of the text. And so if some of the pattern wouldn't even fit within the text, within the end of the text, well, then clearly it's impossible we're going to receive a match, right? So we should just terminate the algorithm there and not waste any other comparisons. So I'm going to go straight to the viz tool, and we're going to talk about, and we're going to go through an example. Alrighty, time to go to the viz tool. All right. So I added a cool. So I added my little face cam here so you guys can see me while I'm talking about these, because I'm going to spend more time on here than I did with sorting. Besides that, now what I'm going to do is I'm going to go over here. So my pattern in this case is ghost, and my text is go gob ghost. Right. So we're going to see right here. First, I'm going to hit play, or I'm going to hit step forward. So it's going to compare G. It's going to compare G and the pattern with G and the text. That's going to be a match. Cool. So I can see that. I increment J. So now I'm comparing H and H. That's also going to be a match. Cool. I compare O with O. Also a match. Cool. And now I realize I'm also at the first point, I'm going to have a mismatch. And a mismatch right here in brute force, very, very simple. All I do is increment I, right? So now we see that now I was before 0. Now there's an indent of 1. And then I just reset J to 0. That's why I'm recomparing this character right here, G, with H in the text. So this is going to be a failure. So we're going to fail there, and we do the same thing. We chug again. Right, I chug by 1, and so now I is going to increment. G slides over, ghost slides over by 2 now. It's composed to the center. And then I'm recomparing G with O. Once again, that's going to be another failure. Cool. So now I go again to chug. I chug by 1. And now I'm going to get, this comparison is going to pass here. Cool. I'm going to go on to the next character. I'm going to increment J. It's going to go to H. H is not going to match O. So you can probably tell what's going to happen here. This comparison is going to fail. And then from there, oops. Can you explain what J is in this intro part? I'm a little confused about how it's different from I. Cool. So good question. So in this case, I is going to be the indent, right? So right now, I is 0, 1, 2, 3, right? Because ghost has slid over 3 boxes over here to the right, whereas J is completely different than I. J is the character in the pattern that we're comparing. So right now we're comparing character H in the pattern. So right now J would be 1, right? And so then we are always comparing the pattern at J, so right now H, to the text at I, which is 3, plus J, 1. So 3 plus 1 is O right here. That's why we're comparing I plus J in the text to J in the pattern. Hopefully that makes sense. Cool. Here, H, unfortunately, does not equal O. So I'm going to get a mismatch here. I get a mismatch here. I chug again, reset J to 0, lose all my progress. And you can see this is fairly inefficient. I'm calculating, I'm comparing the same characters, I'm comparing the same characters in the text multiple times, right? And almost to no avail. So now I'm going to comparing G against O. That's also going to fail. Boom. So I chug again, increment I, reset J to 0. B also is not equal to G, so I do the same thing again. Boom. So now I reset, I increment I. So now I is going to be 1, 2, 3, 4, 5, 6. Cool. It slid over 6 spots in the text, and J is going to be equal to 0. Cool. So now this comparison is going to work, as you can probably tell. So I stays the same, J increments. This comparison works as well. I increments. Or sorry, J increments, not I. And then from here, J increments as well at O. Cool. J increments again because S passes. J increments again because T passes. Cool. And then from there, I am done. So now I found the first match, the first occurrence of my match in brute force. If I was searching for all occurrences, well, I just treat it as a mismatch. And so all I would do in that point is I would do the same thing. I would say I would increment I and then reset J equal to 0. So that's kind of how brute force works. Not really any optimization at all. You basically just kind of bludgeon through the text until you find matches. So I'm going to wait for a second, see if there are any questions. If there are not, I'm going to move on to the efficiencies for the algorithm. Okay, no questions, so I'm moving back to my whiteboard. Cool, now I'm moving back to my whiteboard. So now let's talk about the efficiency of brute force. I'll make sure it's cool. Let me talk about the efficiency of brute force. I'm moving my iPad so I can see if questions are being asked. Cool, how am I doing on time? 6:15, nice. Okay, cool, brute force. So kind of we realized that our best case really for brute force is honestly, let's assume a situation where the pattern is there are no mismatches at all, right? So that would be a scenario where if we thought of like our text would be something like, actually it would be a situation where it failed on the first character. So our text would be A, dot, 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 A, and our pattern would be B, A, or something like that. And so what would happen every single time would be that we compare A or B to A, it would fail. And so I would immediately chuck, right? And by doing so, at most, I'm going to fail on the first, I'm going to fail with J equal to 0 every single time. And by doing that, basically, I don't do any excessive comparisons because I'm never comparing one character in the text more than once. And by doing that, if I'm going to compare every single character in the text exactly once, well, now it'd be a case of where the complexity would be O of n, right? So the best would be O of n. Note that this is for all matches. Actually, this is for, no, sorry, this is for single match. No, this is for, it'd be O of n if I was looking for all matches. I think, let me look at my sheet just to make sure. Yep. Oops, wait, where is it? Yep, exactly. And then also my efficiency for the best case if I'm searching for a singular match, well, that would just be O of M, where M is the length of the pattern, because then I would have a case where, imagine if this was a B now, then I would just match on these three characters. I compare three characters, that's how long the pattern is. And so that case, the best case would be O of M. This is for a single match. Now it's probably easiest to move over to the worst case. And the worst case for this algorithm is actually going to kind of be the opposite case. So this was relative to kind of the best case. So now I'm going to go for the worst case. It would be something like this. It'd be where the text is still A, dot, 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 a bunch more A's, A, right? But the pattern, now instead of the pattern failing on the first character, it's actually going to fail on the last character, right? So what's going to happen here is I'm going to compare, I go question? Nope, I think it's just different channel. So from here, what's going to happen is I'm going to compare this A with this A, pass, this A with this A, pass, this A with this A, pass, until I get to the very, very last character. At the point I've reached the last character in the pattern, I'm almost at a match. I've compared M minus 1 characters in the pattern. Then on that last character, on the nth character, and M minus 1 character, I will fail. That comparison will fail. And by doing that, I have to chug by 1, and I reset J all the way back to 0. And so then the pattern would look something like this, where I could pass all of these again, the M minus 2 comparisons, and then the last one I'm going to fail. And by doing that every single time, for every single alignment in the text, I'm doing approximately M comparisons. And so for every single character in the text, I'm doing M comparisons, and there are N characters in the text. I'll end up doing O of M times N work, right? Which is not very, very good at all. I have a question from Piazza. Let me look at that. Best case efficiency, brute force. The best case should be O of M if the pattern matches the very first index in the text. Exactly, right. But that's if we're looking for only the single occurrence of the pattern, and a single occurrence of the pattern in the text. If for some reason we want to look for all occurrences, and let's say the pattern was A, if it was like 5 A's and the pattern was 100 A's, well, I would do 5 comparisons to get the first match. And then again, I would have to, after that, after finding all occurrences, I would chug I would increment j back to 0, and then I have to do 5 more comparisons, and so on and so on and so on. So I would actually arrive at O of m times n in that case too. So best case for only one match is O of m, you're correct, but for all matches it's going to be O of n in the case of where I fail on the first character of the pattern every single time. So thanks for that question, good input. Now I move on to the average case. And the average case for this algorithm is actually going to almost always be O of m times n, right? There it is, O of m, O of m n. Because in general, I'm going to be recomparing characters that I've already seen before, right? And so in that case, what's going to happen is because I'm comparing characters at potentially more than one time, and I'm chugging by one only every single time, it's going to converge to O of m times n, right? Hopefully my earbuds just kick out. Hopefully people can hear me. Mention in the chat if you can't. Hopefully they didn't just go out. That'd be a problem. Okay. All right. So now let's talk about Boyer-Moore. I think they may have cut out, but I got to keep going. Okay. So Boyer-Moore is the next algorithm we're going to talk about. So Boyer-Moore aims to improve upon brute force by skipping more characters in the text in the event of a mismatch. So it does this by pre-processing the pattern to construct the last occurrence table to realign the pattern much more optimally. So there are kind of two parts of Boyer-Moore. The first one is constructing this last occurrence table, and then the next part is the actual algorithm. I'm going to run on my computer and just make sure I didn't lose the stream, because that would not be good. Nope, I didn't lose it yet. Okay, cool. I don't know what happened with my AirPods. It made a funny sound and I thought it died. Okay, so the first part is constructing the last occurrence table, and that's what we're going to kind of dive into first. I actually did the algorithm on this slide, so actually the last occurrence is going to be on the next slide. So the last occurrence. Last occurrence table is actually really easy. Basically, we're just mapping every single character in the pattern is mapped to the index of its last occurrence in the pattern, right? So let's think about what that means. Let's think about if I have a pattern, something like A, B, C, A, or something like that. Well, initially, if I'm considering I'm going from the front to the back of the pattern, initially the last occurrence of A in the pattern is 0 until I reach over here A again, and I have to update the last occurrence of the character A to, in this case, 0, 1, 2, 3. It would then be 3, would be the last occurrence of A. B and C only appear once, which is fine. So their last occurrence is never going to get updated, but A's will because it appears multiple times. Cool. So maybe thinking to yourself, what kind of data structure would be most optimal for me to kind of store and create and construct this last occurrence table? Mapping, buzzword, yes, it actually applies to a hash map, right? It applies to that situation where you're trying to map a character, A, B, C, D, whatever, to an integer, right? 0, 1, 2, 3, 4, whatever, right? So if you're asking yourself, should I use the hash map? The answer is certainly yes. Cool. Question? Nope. Someone asking something in a different channel. Nice. Okay, cool. So now I'm going to iterate through the pattern, placing each character in the table or updating its last occurrence if the character exists multiple times. That was the case I mentioned right over here above, where A appears multiple times in the pattern. I have to update its value in the last occurrence table if I saw it again. So kind of two methods that are useful in this situation, right? Well, if we want to think about the use case we're trying to do here, if the character does not exist in the hash map, well, I want to place it and use the most current index, whatever I'm at. However, if it already is in the table, well, in that case, what I want to do is I actually want to overwrite that value. Well, that's actually exactly what put does, right? What you implement in your hash map homework. Put, if it's a new value, it'll place it in there with its key value. If the key already exists, it'll overwrite the value to the new value. So put's the first method you're going to want to be using in your hash map. The other one is something called get or default. And we're going to be using get or default to detect if that key is already exists in the hash map, right? You may be saying, okay, well, I could use get and, depending on what it returns, maybe if I just call get and it returns something or throws an exception, then I can try catch that and then use that to tell me if something's already in the hash map or not. Don't do that at all. Get or default is actually a very, very useful method in hash maps. And basically what you do is the first argument right here, this would be a character. right? This is a char. And then the second argument is what you want the default value to be. In this case, it's an int. So basically, this is the value that it's searching for, just like a normal get call. And this is the value that you want it to, this is the value you want to be returned if that key does not exist in the hash map. So if I were to call get or default of D on this pattern, well, D doesn't exist in the last occurrence table at all. So it would actually return a default value, whatever I just specified the default value to be, right? So using that information, get or default, using that information, we can construct our last occurrence table. All right, so I'm going to go over to the viz tool, and I'm going to go over one of these examples to show you how it works. Alrighty, here we go. I'm going to the viz tool. Nice. Alrighty, so I'm done with this one. I'm going to head over here. So my example today is Shanghai. I'm going to be constructing the failure table for this. Cool. So we're going to start with S. So in our last occurrence table, S does not already exist. So I'm going to place it with the default value of I. All right, cool. I'm step forward. Now I see H. This is the first time I've encountered H. So by calling put with H, I'm going to put it with a value of 1. Let me check the thing really fast. I'm worried about something in Slack. Where is this? Yeah. Okay, cool. Yeah, so I'm just going to keep on calling put every single time, and I'm just going to be calling it with the value of whatever I is at that current index. Cool. So now go over here, A. I'm going to place A with whatever I is at that point. I right now is 2, so I place that into my hash map. I go to N, it's the first time I've encountered N, so I place 3. G, same thing, I've encountered a 1, so it's 4. Now, something interesting is going to happen with H. I'm going to call put on H with a value of 5, and it's going to it's going to overwrite this value of 1 in the hash map. Yep, right there you can see that. It's going to do the same thing again with A. So now A's last occurrence of 2, which we found at this point right here, is actually going to be overridden by the A we find right here. So this 2 is going to be updated to a 6. Cool. And the last one is I. We haven't encountered an I before. I'm going to call put of I and actually the variable I, which is marking wherever we are in our pattern. So I is going to put in there with a pattern of 7. Last occurrence table, not too challenging. Really, you're just calling put on every single index in the pattern and putting in the last occurrence table and then returning that at the end of the method. Not super complicated, not rocket science. If I have any questions on that, I will look at them. But if not, I'm going to go over back to the whiteboard because the actual algorithm is much more complicated than the last occurrence table constructing that. Cool. Okay, so now we're back. Cool, so I'm going to go back over here to, oops, I got a question. Let's see. What is the char and getter default? Again, I heard that default int is the value to return if key doesn't exist, but what does the char represent? So getter default is actually going to be the value you're going to be using in the actual algorithm. I'll reference that a little bit later. I was being silly, and I was thinking that it was referencing something in the last occurrence table, but I was just brain dead from the past couple hours. So yeah, getter default is actually going to be used in the algorithm for Boyer-Moore, but it's not going to be used when you're constructing the failure table. Cool. So yeah, so just to clarify, you only need to call put when you're constructing the last occurrence table. We're going to be using get or default now that we're going to be in the algorithm of Boyer-Moore, which I'll explain in just a second. But yeah, good catch. I slipped up. Okay, cool. So the kind of the general procedure with Boyer-Moore is that we're going to be attempting to kind of slide the pattern along to realign the character that we mismatch in the text with the last occurrence of that character in the pattern. So kind of how that works. Honestly, I don't find the pseudocode that engaging. I find it more stimulating to show it in the viz tool, which I'm going to do in a second. But I'm going to go over the pseudocode at least briefly once to kind of show you guys the gist of it. So now with Boyer-Moore, we actually start comparing from the back of the pattern first. And what that means is we're going to be assigning j to pattern length -1. And then as long as the pattern hasn't extended past the text, that's the same while loop check as we were using in brute force earlier. What we're then going to be doing is comparing pattern of j at text of I plus j. That's the same check we were doing earlier as well. And every single time we get a successful comparison, we're going to be decrementing I. Or sorry, not decrementing I, we're going to be decrementing j. Right, so that's just representing going from the back of the pattern towards the front of the pattern. And if we ever reach a time where j is equal to -1, well, that means we just successfully compared the character at j equals 0. If we've successfully compared the character at j equals 0, since we're going backwards from back to front, that actually means that we've found a match. And so if we ever encounter j equals 1, we can add that index to the list that we're going to eventually end up returning at the very, very end. Okay, if you get a mismatch, you're going to get a realignment from the last occurrence table, right? The last occurrence table, so we're trying to get the character that we failed at in the text. The character that we failed at in the text is going to be located at text of I plus j. And so every single time I'm denoting these, just for reference, when I'm denoting the text or the pattern with these arrows or with these brackets, I'm kind of representing it, indexing kind of looking like an array in Java. But for you guys in your homework, you actually be using .char at instead of indexing it like an array like I'm doing here. I just did this because it's much cleaner. Cool, so to get the last occurrence of the character in the text we mismatch on, we're going to be calling .get on the text of I plus j. But what we actually want is let's assume if the character is in there, that's awesome. But if the character is not in there, this is when we want our get or default value, right? In this case, our default value is -1. So instead of calling get like this, I'm actually going to overwrite this. I'm going to call last get or default, and this is text at I plus j. I don't have room, so I'm doing I plus j, and then our default value is going to be 1, right? So instead of calling .get, and then we have to kind of try catch if we didn't have a key there, if that key didn't exist, that'd be the instance of, like, let's say our pattern had an x, and an x didn't even exist in our pattern, or sorry, our text had an x, but our pattern did not have an x to begin with. Then that would be a case where x would not exist in the last table at all. Well, the good news is that by using get or default, it would return -1 to us, right? Because that's the default value. That's the value we want returned if that key doesn't exist in the hash map. So that's exactly what will happen. So if the value is, or sorry, if the key is in the hash map, if the character at I plus j in the text is in the hash map, we're going to return that index that we mapped to it earlier. If it is not, we're going to give it back -1. And we'll see why we give back -1 in a second. Okay, so now we check if the alignment would cause the pattern to shift back. And the alignment that we check is we basically are checking is I'm gonna call whatever this last occurrence I get or default. I'm gonna call this shift. This is equal to shift right here. So we're just checking if shift is greater than j. I think. Let me make sure. I don't want to tell you something wrong. If yeah, okay, cool. If the shift is greater than j, then basically the formula we use is I plus or equals j minus shift. If shift is greater than j, what will happen is that actually what will happen, it's like, let's say j is 3 and shift is 4, where then I is going to add 3 but then subtract 4. And that would cause the indent of the pattern to actually go backwards relative to the text. If that ever occurs, we don't want that. In that case, we actually continue to just chug by 1, right? Because we never want to slide the pattern backwards, right? That could cause infinite comparing. So what we actually do instead in that case, if we get to a situation where shift is greater than j, we chug I plus plus, and we set j back to pattern length -1, right? We really don't have anything to work off of that point. That means, and that's the situation where we've already passed the last occurrence of the character that we failed in the text. So we can't slide back the text to get to that point. You'll see an example in the viz tool. It'll make more sense there. Otherwise, assuming the shift doesn't cause the pattern to go backwards, we're going to use I plus equals j minus shift. Right, so what that means is j minus shift is basically saying whatever the current value we're at, we're shaving off the shift, and that aligns the beginning of the text with that character that we mismatch in the text with, right? So we're realigning the pattern that we mismatch with in the pattern, or sorry, in the text. Now we're realigning that last occurrence of that character in the pattern with that character that we mismatched in the text. I know I'm fumbling around with my words a little bit. It's a lot of notation. Cool. So, but really the main formula for you to grasp here is I plus equals j minus shift. If you can really lock down and master that, then Boyer Moore comes very, very simple, very, very fast. Another thing that's, and so basically what this does is it utilizes the character that we mismatch in text with the last occurrence of the character in the pattern. That's the words that I fumbled a little bit earlier. I'll say it one more time just to be clear. This aligns the character mismatched in the text with the last occurrence of that character in the pattern. And that's exactly what we're trying to do here. Also notice that if we get a default value of -1, what actually is going to happen is that Boyer Moore is going to shift the entire pattern all the way past that character, right? Let's think of a situation of where J is on the very, very last character in the text, right? It's let's say the length of the pattern is 4, and the length of the pattern is 4, and we mismatch on that last character. If that character in the text didn't exist in the pattern at all, what will actually happen is that the formula will do I plus equals j minus shift. So I will add 4 and then minus 1, i.e. 4 plus 1 is 5. And so what that'll do is it'll shift the entire pattern past that character in the text. And that's where Boyer Moore really, really shines, is when it can skip a bunch of characters in a row. So I know this is kind of a jumbled mess, and so that's why I'm going to show you more examples on the viz tool, and it'll probably make more sense. So I'm going to head over there now. All right. Let's go over here to our super cool viz tool. My face is there. You can see me. Cool. I'm going to go on to the next tab. Boom. We have a big pattern and mildly sized text as well. So I'll give you a second to kind of write that down. But first, we're going to be covering the last occurrence table of this pattern. So I'll give you a second for that. Maybe look at my super cool iPad to see if there are any questions. If there aren't, that's fine. My iPad's still making funny noises, making it sound like they died. I guess not. Who knows? Okay. So now what I'm going to do is I'm going to, hope you've had a chance to write down the pattern. Don't worry if you didn't get it. You can always pause the video later, catch up, or you can watch it on demand once we upload it to YouTube and Canvas. Cool. So I'm going to step forward here. Last occurrence of A. I'm kind of going to bludgeon. I'm going to go super fast through this because we already seen it. Okay, haven't seen A. B is 1. A will get overridden to 2. C hasn't been seen before. It's 3. A will get upgraded to 4. B will get upgraded to 5. It's more recent. And then A will eventually get overridden to 6. Right. So going into Boyer Moore, we finally constructed our last occurrence table. It's going to be A is mapped to 6, B is mapped to 5, C is mapped to 3. Cool. Now let's place our pattern over here. So 1 second, I'm going to get some water. Talking for 40 minutes, even for me, makes my throat dry. Cool. All right, so notice how we're comparing from the back of the pattern as opposed to comparing from the front of the patterns. We're doing different algorithms. This is the only algorithm where you get to compare from the back, so enjoy it while you can. We're going to be carrying A and A. They both match, so you'll see that me decrementing J. Cool. So J is decrementing, so now I'm comparing J in the pattern, B, with I plus J in the text, C. We're going to get a mismatch here. So now what we're going to try and do is we're going to realign the pattern with the last occurrence of C in the text, right? So now if we look at our formula, what's going to happen is right here is we're going to look, C is mapped to a value of 3. And then now when we see this, what will happen is that J at this point was pattern.length of 1, 2, 3, 4, 5, 6, 7, minus 1 is 6, 5. So what we did is 5, I plus 5, right? And then I subtracted off 3 from it, right? Because C had this value of C right here. And you can see what we've done now is we've aligned C right here in the pattern with that last occurrence of it in the text. So now we can see we're back to comparing to pattern.length minus 1 again. We reassign J to be pattern.length minus 1, and we go for it again, right? Cool. A matches. We're going to get a mismatch right here. And now you're going to get to see the most impressive part of Boyer Moore, where it really, really shines. It shines because D does not exist over here in the last occurrence table. So what we're going to see is we're going to get a -1 value. This is kind of represents the default value for D. the getter default. So in this case, getter default will return to you -1, right? And we generally represent this with an asterisk. And what we'll see right here is that it's going to shift the pattern all the way past D right here. So that now it aligns right. I just twitched it. I thought I saw something in the hallway, but I guess not. Okay, cool. So you're going to see right now the pattern is going to completely shift past this character D, because we know that if we had an alignment right here, any alignment where D touches anything in the pattern, well, clearly there's never going to be a match because D doesn't exist in the pattern to begin with, right? So now we're going to see if we step forward, it's going to move all the way past D in the text. And now we see that it moves just past D in the text, right? And that's the first time there might be a valid alignment of the pattern, and we could get a match, right? The first time. We know that anything, even if A was right here, even if it made it to the last character, there's still no possible way it can get a match because D doesn't exist in the pattern at all, right? So that's why we skip all the way past it. Cool. Now I'm going to compare again. This fails right here with B. It fails right here with B. It fails in the last character. We really don't have an option. We just chug by 1, right? So you see me chugging. I just increment I by 1, and I'm going to reset J to pattern on length -1. Cool. I compare A. Cool. That's awesome. B also passes again. I keep on decrementing J. Passes again. A. B. Okay. This is going to be the part where we're actually going to chug instead of realigning the pattern. Note that we've already correctly compared an occurrence of B. So now we're at another occurrence of B. So now if we were to try and realign the pattern like this, last occurrence of the table is B is equal to 5. Right now, J is equal to 0, 1, 2, 3 in the pattern. So what would happen is if we were to try and realign this B in the pattern with this B in the text, the pattern would actually shift backwards, right, to the point of this over here where it would be A, B, A, C, A, B, A. Well, the pattern can't shift backwards. That could result in infinite comparisons. So in this case, we don't have anything else to base we don't have any other information we can utilize here. So our only option, we're forced to just chug by 1, right? And we're forced to just have I increment and reset J to pattern length -1. Cool, so I'm gonna step forward, it does that. Now I go over to here to C, this fails in the first one. Start to go a little bit faster because time is of the essence. Cool, so now we're gonna get to a time where I get to this passes, this passes, this passes, this passes, this passes. You guys see what's gonna happen here. I'm gonna get a full match. And the cool thing about Boyer Moore is that in the event of a match, all I do is just chug by 1, right? I don't really have any information I can base off of. So all I have to do is increment, doing the same thing that I do in the event of a mismatch, like if J is equal to pattern length -1. If I reach a match, all I do is just increment I, reset pattern or J to pattern length -1, and go from there. Cool. So I'm gonna step forward. You're gonna see that right here. A does not equal B, unfortunately. And now we're gonna see that if I were to realign this again, ABA, CABA would actually be 1 skewed over. This A would be hanging off of the edge of our text. If that's possible, if that happens, there's no way there can ever be a valid match because I can't even compare all the characters in the pattern to the characters in the text. So we know at that point the algorithm terminates. There's no further reason to do any other comparisons. Cool. If I get any other questions about Boyer Moore, I'll happily answer those. If not, we're gonna go to efficiencies relatively fast, and then I gotta cook it and do KMP. So I'm gonna move over to that right now. After I get a sip of water. Alrighty. Cool. No questions, it looks like, which is good. Forgot my marker, which is not good. I'm gonna go over here and grab it. Cool. So now let's talk about efficiencies. I'm gonna go back a slide. Hopefully, I got everything over here. Oops, that is the wrong one. With the opposite direction, decremented I instead of incrementing I. Cool. So now I'm back over here with the Boyer Moore slides. Best, average, and worst case. So let's talk about the best case for Boyer Moore. So the best case of Boyer Moore is kind of going to be in a situation where the best case for Boyer Moore is going to be in a situation where it's similar to before. If I'm looking for the first occurrence of the pattern in the text, Well, in the best case, it's going to be O of M, right? Because that's just the case of where every single character in the pattern matches with the text, right? So this is for one occurrence. For first, cool. And then otherwise, the best case is going to be, if I'm finding all occurrences, is actually going to be something a little bit funny. And I don't know how much I'm going to have to explain this, right? It's actually be O of n divided by m plus m. So the O of n divided by n actually comes from, let's imagine that the first character or the last character in the pattern. So let's give something like a x, and then the text is just a. I don't know how readable that is. Hopefully, relatively so. What will happen is actually, oops. Sorry. This should be the. I don't know why I did this. Okay, cool. Instead of the, I'm actually gonna make the pattern something like a, and the text is something like b, 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 b. So what's actually gonna happen is I'm going to fail on this first character right here, this first comparison. Got a question? What do you mean by two hash map methods is useful? So one, put is gonna be useful for, this was from a long time ago. Put is useful when I'm constructing the last occurrence table. Getter default is useful when I'm actually utilizing the last occurrence table in the actual algorithm for Bournemore. So in last occurrence table, basically all I'm doing is just calling put on every single character in the pattern. And getter default, I'm basically trying to retrieve a value from the hash map if it's there. If it's there, great. I want that value. If not, I want the default value of -1. So that when I do that, I can shift past that entire character in the pattern. Nice segue into what I was talking about with the best case is that if I miscompare A and B, well, B doesn't exist in the last occurrence table at all over here. So what I'm going to do is I'm actually going to shift the entire pattern all the way past this one, right? I'm going to compare it all the way past it. Same thing's going to happen over here with a bunch of more Bs. This is going to pair it with this, and I'm going to shift it all the way over. Well, that means that for every m characters in the pattern, I'm only doing one comparison. So that's n divided by m. And this plus m over here comes from the cost of constructing that last occurrence table. I'm doing it for each character, m characters plus m. That's all I'm going to have really time to talk about over here. Does more and more only work for single occurrences? No, it works for multiple occurrences. I mentioned that over there in the viz tool. If you're doing multiple occurrences, every single time you get a match, in that case, all you do is just increment I, so I++, and you reassign j to pattern on length -1. This is for all occurrences. I really got to cook it, guys, because I want to make sure you guys get to KMP. Cool. Average case. Average case, blank. We don't really talk about average case for Bournemore. I don't have time to discuss it right now, but really, it's very, very dependent on the relationship between the pattern and text, so much so that it's difficult to really say what the average case would be. We wouldn't ask you this on a test, so don't have to worry about that. If you want to, you can explore it more. But really, the average case for Bournemore is very, very text pattern dependent. So we don't want to give you a formal answer because it's not super fair. And that comes from basically the same character in the text could be compared more than once. And because of that, there's no definitive way to construct an average case due to that. That's all I'm going to say on that note. And then we have the worst case. Well, what is the worst case? Well, that would be a situation where I have something like I have something that my pattern is all A's, and my text is something like this, right? So this passes, this passes, this passes, this passes, boom. And then I get to a point of, well, I don't really have an option, and then I just move this over by 1, right? And so the same thing. I'm going to start comparing from the back again. Boom, 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 boom. Get here. I don't have an option. So basically, every single time for I'm going to be doing, it's going to divulge into O of m times n again. It's not great. O of mn. And yes, you could tack on the extra cost of the construction of the failure table, but mn is going to dominate just the cost of m, as m and n both grow large. So that's all I'm going to touch on that. Basically, it's going to fail on the first character of the pattern, and by doing so, it can just chug by along. It's going to chug along by 1, and it's going to have to recompare all m characters again to get back to that first character again. So Bournemore works better when the the relationship between the pattern and the text is that the text is very, you want failures in Boring More. You want to get in situations where you hit characters that don't exist. When you hit characters in the text that don't exist in the pattern, because in that case, you can shift all the way forward and reach that best case that I talked about over here. So when the relationship between the alphabet of the pattern, the ratio between the text and the pattern alphabets is very, very high, i.e., the pattern has a lot of characters, like say all 26, and the pattern only has like 3. Well, that's going to be a very, very fortunate case for Boring More, because you're going to get into situations where you get to skip a whole bunch, which is super awesome. So all I'm going to cover on Boring More, I need to get going. 6:50, so I got 25 minutes to cover KMP. Cool. Newton Morris Pratt, also known as KMP, improves upon Boring More by improves upon brute force by doing a different approach. It's actually going to utilize matching the prefix that is also a suffix in a pattern, so we don't compare characters that will undoubtedly be correct. And so that comes by, again, a cost of pre-processing the pattern. And now instead of processing a last occurrence table, we're actually going to process something called a failure table. We'll see how to do that in a second. Actually, it's just right below, right? Don't worry about how we're going to be utilizing the suffix and prefix right now. We'll do that in a second. So basically, here's a pseudocode for the failure table. It's really right here. We give this to you as well in the Sci-Christian slides. The Sci-Christian slides, side tangent, fantastic for pattern matching, almost better than they are for sorting. It's really, really, really good. You should definitely check that out. So what we want to know with this failure table is that actually the end index has the length of the largest prefix that is also a suffix of the pattern up to that point. What the heck does that mean? Well, that means that I get into a situation of, like, let's say if I had something like A, B, A, B, A, right? The first is always 0. B, if I was looking at B just as a suffix if I was looking at B as a suffix of AB, the characters we've encountered so far, there isn't any overlap. So B would also be 0. If I look at A, however, well, A has a common prefix suffix with this right here, right? A is also a prefix of this part of the pattern. So A would have a value of 1. Now if I look at B, well, AB is actually a prefix. This suffix is actually shared as a prefix also in the pattern, right? So it's this and then this, right? So B would have a value of 2. Then I go to A over here, and I actually realize that ABA is a common suffix of also this very large prefix of ABA. So ABA would also have a value, or ABA, this A right here would have a value of A. And so really what's happening, that's going on here, is that to calculate this, it's a funky little algorithm of where you start with I is equal to 0, J is 1, and you go until J is past length of the pattern. What's happening here is that if pattern of I is equal to pattern of J, right? So that would be a situation like right here, or a situation right here. What's going to happen is that the failure of J is equal to J, or is equal to I plus 1, right? So if I is 0, I'm going to be assigning I plus 1, 0 plus 1 to this value in the failure table. Cool. I'm going to increment both I and J. So then it would be pointing over here to this B and B. Otherwise, this is a match as well. So I'm going to increment, oops. Is this, what's going on over here? Let me look back at my notes for a second. Right, I plus 1 to failure J. I'll return to that when I see it in the Viz tool. Okay, so, and then other circumstances. If I is not equal to 0, then we can actually utilize the failure table, and we can reset I to be failure at I minus 1, right? So this utilizes the suffix prefix that's already been computed. And we'll see an example of that in a second in the Viz tool. Otherwise, we assign failure of J just to 0, and we increment J. Because at this point, we don't really have any, there's no way that we can't utilize, we can't do, there's nothing to utilize. I can't go back and reset I because it's already 0. I is already 0, so I can't index I as -1 in the failure table. So I just assign J 0 at that point, and then I increment J. Okay, cool. Remember wondering, that sounds super confusing. It's mildly confusing to me as well, or like especially when I first took the course, I think it's much more helpful to go over an example and then really dive into it there. So I'm going to do that right now. Feel free to ask me questions on the Viz tool as you see fit, or right now as you see fit. I think that especially the failure table is super hard to think about without seeing it in action first. Oops. Over here, I'm going to go to my Viz tool. Nice. Okay, cool. A failure table. Okay, so my failure table right here. I and j denoted here. There's a mismatch here, but I is equal to 0, so there's no other option. So I just have to assign b to also a value of 0. Cool, so we'll see that right now. Okay, I and j match, so I'm going to assign this the value of I plus 1. So this is going to be 1 now. Cool, I increment both. Now I get to a point of, oh, I see what I did earlier. I incremented both I and j. I forgot to do the failure right there and then reassign I earlier. Won't have time to show you. Maybe I will, but we'll see. So now b is not equal to a. Cool. So I'm actually going to assign I equal to failure of I. Right, we'll see here. I reassign this back over here to a. Cool. So that's the step. Let me make sure I'm getting that correct. Where is the? My paper's all in this. Yeah, so I'm updating I. So at this point, I was 1, and I'm updating it I minus 1, and I'm looking at that value in the failure table and reassigning that value to I. Right, so I looked up I of 0. I of 0 is 0, so I would still get assigned there. Cool. Then I go over here to A. This is going to pass. Cool. So I'm going to increment, and I'm going to assign this a value of 1 as well. Cool. Now I get over here to B. B, these two match over here. So what's going to happen now is that this is going to get a value of 2. Right? It's going to get a value of 2 because it's going to assign it 1 more than the current value of otherwise fail J. Why am I stumbling on this? Oh, I was equal to 1. What am I talking about? I was equal to 1 over here. So I plus 1 is going to be equal to 2, obviously. Being silly. Cool. The same thing's going to happen here. This A and this A match. I right now is equal to 2. And so then 2, it's going to write I plus 1 to this value right here. I plus 1 is 2 plus 1. 2 plus 1 is 3. So 3 is going to get written right here. And we can see that ABA is this suffix also exists as a prefix right over here. Cool. So we're going to get 3 right there. Nice. That makes sense. This is going to fail, right? So what's going to happen now is I'm going to assign I to be failure at I minus 1. So I right now is 3. I'm going to look up I at this index right here. That's 1. And I'm going to assign that value to I. That's going to give me B, since B is index 1. I maybe didn't mention this earlier, but instead of having this be represented as a hash map, it's actually being represented as an array. And that's why we can index it as such. So you can see here, I will get reset to B over there. Cool. This actually is fine. Nice. So now I can see actually there is a valid prefix of 2 right here, right? A lot of people think that, okay, well, if I mismatch at some point, then I have to reset I all the way back to 0. That's not the case. You can actually continue. You can get a match of a pattern. You can get a match of a suffix, even if it's not. These numbers don't have to solely be increasing or incrementing, right? It's possible for or be 0, right? In this case, we're going to reach a 2 right here. So we actually went up and then back down again, right? And that's completely fine because AB is just as much of a valid prefix right here as ABA was right here. Cool. Now I get to ABA. Same thing again, right? AA match, B right, or sorry, B. I is equal to 2, and so I'm going to increment that value and write that value to A, or the index right here at A. That's going to be 3. Cool. And we see that this was a prefix right here of 3, and this was a prefix of like 3 as well. Now I get here to C. This is no bueno. I'm going to assign I equal to the value at I minus 1. I minus 1 is here. That value is 1. So I'm going to reassign I to be 1 right here. Cool. That's B. That doesn't match as well. I'm going to go back. I is going to get rewritten to I minus 1. The value at I minus 1. The value at I minus 1 is 0. I gets reset to 0. Cool. And then now this still doesn't match. I don't have an option though because I is equal to 0. I can't index earlier in the pattern because I'll get an array index out of bounds exception. So this C just gets a value of 0 written here, which makes sense. There's no valid prefix that ends in a C. There just doesn't, right? Because C doesn't exist until this character right here, right? Cool. Okay, so that's the failure table. I'm going to keep, unfortunately, going kind of fast because there's a little bit more to cover. If you guys have questions, feel free to ask, but I'm going to move over to the whiteboard. Alrighty, let's go back over here. We're going to go to the algorithm. I'm going to stumble. I also managed to forget my pen, so I'm going to go get that right now. Turn my iPad. You can see questions. Now we're back. Okay, cool. KMP algorithm. Now we're back to comparing from the start of the pattern again. We're comparing from the start of the pattern instead of from the back of the pattern in Boyer Moore. And we're going to keep comparing the pattern at J and pattern at I plus J while matching and incrementing J after each successful match. This is the same exact thing as in brute force. There's really no difference here. I'm still comparing pattern J, pattern I plus J, until I reach a situation of where J is equal to pattern.length, in which case I've successfully compared the last character of the pattern to the text, and I've actually arrived at a match. If there's a mismatch, right? If there's a mismatch, or actually if there's a complete match, and I'll show you that in a second. But first, let's just talk about mismatch. We'll talk about mismatch first. If J is equal to 0, there's no valid prefix or suffix I can use in that instance. And since there is no valid prefix or suffix I can use that instance, I chug by 1 again, right? Whenever there's no information that I can use, the best that I can do is just chug by 1. Increment I, reset J to 0. That's all I can really do. That's the case of where J is 0. So that's the case where I compare incorrectly on the first character in the pattern. Otherwise, assuming that I didn't mismatch on the first character, I'm going to reassign J, or I'm going to reassign I to be I plus, or I is equal to I plus J minus the failure table of J minus 1. You're going to be like, what in the heck is that formula do? It's even more confusing than one in Boyer Moore. It may look like that right now. I'll show you in the viz tool and it'll make a lot more sense. But basically what we're doing here is we're going to realign the pattern so we can utilize the good prefix that we had right before we mismatch. Right before we mismatch is why we use J minus 1 right here. And we're looking at what that value is. Whatever that prefix is at failure of J minus 1, we can utilize that and we can use that to indent the text so that we don't have to actually compare those values. So that's the indent of I, but now we reassign J to be equal to fail of J minus 1. And so that means that J is not going to start comparing at 0 like it would in brute force. It's actually going to start comparing directly after the perfect prefix that we found in the failure table. And this is utilizing the valid prefix suffix from the failure table. You may be asking yourself, okay, well, what about all occurrences of the pattern? The funny enough, in KMP, it's actually not an edge case at all. Really what happens in Boyer Moore is that you treat it like that there was a mismatch on the last character. The last character in that case would be J is equal to pattern length. So actually you're going to treat it like there's a mismatch on the last Can everybody hear me now? Can everybody hear me now? Hopefully. Can someone in the chat just let me know in a second? Hopefully they can hear me. I'm trying to use my mic. Yes, we can hear you. Yay, let's go. Okay. Alrighty. Almost done. Sorry for that. I guess my AirPods finally did die. I know the mic quality is probably not going to be as awesome as it was when I was using my AirPods. We're still going to bludgeon through it. Okay, cool. So I'm going to do my failure table super fast. I have it up right now. So what's going to happen is, oops. Oh, I already did this one. Cool. Okay. So I'm going to calculate my failure table first, right? So over here, B is not equal to A. This is going to get a value of 0. This is going to get a value of 1, 0. In a second, this is a value of 1, 2, 3, right? So this is from a prefix of this A. This A is from a prefix of this A. This B is from a prefix of this AB and this AB. And this ABA, prefix of 3, is linked to this prefix right over here of ABA. Cool. All right. Now we're going back into the actual algorithm. Nice. Okay. So ABA. So this is going to match. A is equal to A. Cool. B is equal to B. A is equal to A again. Now we get to C. Right? Now we're going to look up whatever J minus 1 was in the failure table. J minus 1 in the failure table is actually going to be this value right over here. Right? It's going to be 1. So we're going to see that I is going to be equal to I plus equal J minus that value. So it's going to be, right now, J is equal to 0, 1, 2, 3. So it's going to be I plus equals 3 minus 1 of 2. So this is going to slide over 2 elements. Nice. Exactly, right? And so now we see that right here, after that, we're actually going to reassign J to be 1, right? And that shows that now, instead of comparing right now in brute force like we would have earlier at this character, well, we already know there's going to be a match there because there's a valid prefix. So in that case, we skipped over that character. That's denoted by the yellow right here on the viz tool. And we're going to compare with B and B over here. Even though we didn't know that that was going to be a match, what we did know is that there was going to be this prefix of 1 character. We wouldn't have to compare anything there. Cool. So B is equal to B. Cool. This is equal as well. C. Match. B. Boom. This is a mismatch, right? What we're going to see now is that B was a mismatch right over here in this character. So now we're going to reutilize this prefix of A right here, and we're going to benefit from that prefix. So right now, J is equal to 0, 1, 2, 3, 4, 5. 5 minus 1. So this is going to be offset by 1, 2, 3, 4. So then the first A is going to be right here. Cool. It's the same thing. We're utilizing that same good prefix, right? And so even though I made it through a lot of characters, I'm keep on moving the pattern forward. And we're seeing that's a very awesome part of K and P. So I compare B and D. They don't match each other. I look up. I try and get some amount of benefit out of the shift here. A, unfortunately, is 0. So I'm just going to end up choking by 1 right here, right? There's no benefit that the failure table gave me in this standpoint. D again, I'm going to fail again. This is the point where I fail in the first character, and KMP, there's nothing you can do in this instance. So I'm just going to chug by 1, right? So it's going to be I plus plus. I'm going to reassign J equal to 0. Nice. Okay. A is going to be equal to A. Cool. B is not equal to A over here. I'm going to get no benefit out of the pattern as well, or out of the thing as well, because there's no good prefix up until this point. So it's just going to chug by 1 again. Boom. This is the super cool part right here. A is going to match. B is going to match. A is going to match. I'm just incrementing J. I is staying the exact same. A is matching. B is matching. And A matches right here. Hooray! We got a match, right? Super awesome. Now the coolest part is that hopefully it shows in the viz tool. No. Well, yeah, it does. Okay, cool. Basically what we do is we're treating this character right here as a mismatch. And by doing so, we're going to utilize J minus 1 in the failure table. Well, J is right here. J right now is right outside the bounds of the array. When I do J minus 1, J minus 1 is going to be equal to 3. So I can actually utilize this perfect prefix right here, this ABA that's also a prefix here, and I'm going to realign the text so that I start comparing at this character right here. Boom. Nice. And this is the coolest part. After I got a match, I didn't really have to change anything. I just treated the last character, I just treated it like there was a mismatch, and I realigned and got a perfect prefix right over here, and I'm right back to comparing right at the end over here. Okay, nice. Step forward, this is a match, this is a match, this is a match, this is a match. After this, the pattern would extend past the text, so I'm going to stop. But I want to show you how cool it was in KMP, how you can utilize the failure table even after you get a fully successful match. I'm getting hiccups for some reason. Okay, cool. So I'm stepping forward. That's it. I showed you all the cases over there. And notice how, and this is important for the complexities of the algorithm, is that notice how there was no character for which it was green more than twice in the same, or more than once in the same column, right? Even here, I'm always moving forward. I'm never comparing the same character once I've already done one successful comparison. And because of that, the best case, or the average case of Boyer-Moore is actually going to be O of m plus n. And I'll show you that in a second when I get back to the whiteboard. Cool. Back to the whiteboard. Actually, I think I'm actually just going to do it here because the mic is going to be garbo when I'm over there anyways. So let me see if I can, I'm going to get out a tiny little, I'm going to get out a Google Doc right over here. Boom. Actually, I don't want to show, debating what I can do. This is super tacky, but I'm going to write it up here. So in the average case for Boyer-Moore, because of this, because I'm never comparing one character through a successful comparison more than once, comparing through the entire text is actually O of n, right? So it's actually O of n for this part. However, we still have to construct the failure table, although that only takes a cost of O of m. So actually the average case cost of K and P is O of n plus m, right? Super awesome. That's an awesome best case, or an awesome average case. The best case is the same as it was before. If I'm finding the first match of the pattern, it's just O of m. That would be if the first part of this was abacaba. Well, all I need to do is just compare the first m characters in the pattern, or in the text, and I've already arrived at my first successful match. If not, if I'm looking for all occurrences, well, then it's actually when, it would actually be when the entire, it would be in a situation like where, let's think of a case. O of m plus n would be the best case if, yeah, imagine if I just failed on the first character again like that, like I did before. I'm going to fail on the first character, and I'm just going to chug all the way through the text. That's still O of n. So the worst case, or the best case for Boyer-Moore is O of m. It's for his first match. I'm just going to do O of n, multiple matches. Oops, I don't have enough room. Multiple. Okay, so I just explained that. Now the last one that's kind of the most interesting is the worst case. Well, the worst case is actually still O of m plus n, right? And that's because the logic I just explained, how even in the worst case possible, I'm never going to be successfully comparing a character twice in the text. And because of that, because I'm always moving the pattern forward, I'm doing less redundant comparisons than I'm doing in Boyer-Moore, it's actually going to result in O of m plus n as the worst case as well, right? Which is super awesome. Well, it's going to result in O of n to go through the text, and then cost of O of m to construct the failure table, like I talked about before. The last thing I want to mention before I cut the stream off is why KMP performs well, or like when it performs well. It performs well in kind of the opposite cases Boyer-Moore does. KMP performs really, really well is when there's a lot of overlap between the pattern and the text, when that ratio is very, very small between the text alphabet and the pattern alphabet. When would this occur? Well, one example is DNA sequencing, right? For DNA sequencing, there's only really, I think, 4 or 5 different values that each like genome can be. And so because of that relationship, there's a very, very short ratio between something they're trying to sequence and the pattern of which they're trying to sequence the DNA through.
So in that case, they would use an algorithm like KMP as opposed to Boyer-Moore. When Boyer-Moore thrives more so when there's a lot of mismatches in the text. KMP does really, really well when there's a lot of overlap in the text, and so it can utilize those really, really good prefix suffixes. I'll be here if you guys have any more questions. I know it's super late. I'll stay here for a minute. If you don't have any more questions, I'll cut the stream off in a second. So any last questions, I'd love for you guys to get them in. I'll leave it for, I guess, a minute or so. I'm going to get a drink of water. Once again, sorry about my AirPods cutting out. They were at 100% at about 3 o'clock today, and I guess this was just a little bit much for them today. So maybe they'll be back better next week. Alrighty. So I'm not getting any questions yet. I think because of that, I'm probably going to cut off the stream. One more thing I wanted to say for any stragglers that are still here, the 50 people that are still here. Remember to apply on the TA app if you're interested in TAing for the course. We're going to try and have all of our interview selection done by Friday or so. So please apply on or before Friday so that we can include you when we're making decisions about who to interview or not. Feel free to reach out to your supporting TA as well. We'd love to get recommendations of current students from current TAs. We love getting that, and that can really push you forward in the interview process. To make it so basically we have a vetting process through that. So with that, I think I'm going to cut the stream. Thank you so much, guys, for watching today, and I will see you guys next week. Peace.